morning, everybody. So what I want to do in the next couple of minutes is just to give a general overview of the current status of our HPC communication library software stack, focusing, of course, on UCX, but I will also talk a little bit about OpenMPI and another library that we have been working on called RockShMem, putting it all into the context of our GPUs. And so because of that, I will also start out by saying a few words to our current GPU lineup. And then from there, we'll go to the individual libraries, right? And since, again, most of the work that I'm be presenting here will be within the context of GPU software, just a few words on our current GPU products, MI300X and MI300A. So basically, high-level idea of these GPUs are that they are based on like a chiplet-based approach. So you have individual smaller GPU chiplets that contain the compute units for the GPU, referred to as XCDs. And the MI300X basically has 8 of those XCDs on a single device, surrounded also by HBM3 memory. So this overall leads to like 192 gigabytes of HBM3 memory and 5.3 terabytes of memory bandwidth. So that's like the discrete GPU version. For the APU version, basically what has been done was to replace 2 of the XCDs by some CPU compute dies, the CCDs, right? So basically the MI300A, because of that, has 6 of the GPU chiplets and 3 of the CPU chiplets, again, surrounded by the same HBM3 memory, right? And this is really, I think, like the flexibility of the chiplet design that basically you can relatively easily, everything in hardware is not easy, I know that, but conceptually more easily, basically plug and play and replace individual components to match whatever your current demands are. So the MI300A is basically the chip that is in the El Capitan system. MI300X, again, is more like the standalone discrete GPU system at the moment. One of the, by the way, interesting advantages of this architecture also is that the same chip can be brought up as 1 device, 2 devices, 4 devices, or 8 devices. So the XCDs can basically be combined to individual devices and presented accordingly. And the same from the HBM3 configuration, that the memory can be configured as a single NUMA domain or 2 or 4 NUMA domains, depending on particular user requirements. If you look at the entire node level configuration, MI300X, we have a single configuration that is supported, that's basically 8 devices in a system. Each of the devices is basically configured by 1 direct Infinity Fabric line to every single other device on the node. So basically you have a fully connected network, but because of that, it's hard-coded and limited to 8 devices within a single node at this point in time. For the, each of those devices can have either a separate NIC that they are using, or the system can be also configured, I think, with fewer NICs, depending on customer requirements or other restrictions, right? On the MI300A side, we have a little bit more configurations that we are dealing with. So the configuration, for example, that is used in El Capitan has 4 of the MI300A devices on a single node. And because of that, we can use 2 Infinity Fabric links between every single device, leading to higher bandwidth. Again, typically you will have 1 NIC per MI300A device. Interesting bit that I forgot to mention. So MI300A, really the interesting aspect of that is that you have just a single memory configuration in terms of that both the CPU cores as well as the GPU cores have access to exactly the same HBM3 memory, right? So there's no DRAM at all on those nodes, just HBM memory. All right, now, again, last step in the introduction, just a high-level overview of the RockMaware MPI software stack. So the key components from our perspective or for the configuration that we support is OpenMPI as the main MPI library, utilizing UCX for send receive or one-side put get operations. OpenMPI itself has also support for the ROCm device, and that comes into play for some of the functionality that I will talk later on. Things like pack, unpack, derived data types, and some others. For collective communications, I mean, OpenMPI has support for UCC. UCC has also support for ROCm devices for our GPUs, right? And ultimately, this is the preferred configuration, especially if you are looking at applications that have large reduction operations. I think from that perspective, UCC is our best option for the large reduction operations for GPU memory. All right, now let me talk in a little bit more details about the individual libraries and present some results. So UCX again has support for the AMD GPUs for quite a while. Without going into too many details, so what is required to support the GPUs are things like being able to detect a memory type, right? To be able to distinguish between GPU memory versus CPU memory. You have to be able to perform data transfers, and that's both between host and device memory, but also between multiple devices, right? So that's the difference between the ROCm copy and the ROCm IPC path. And last but not least, you also need support for GPU direct RDMA style functionality, where the data can be transferred directly between the NIC and the GPU. And this is right now working both with the IB Peerman support, but also with DMA buff-based mechanisms, at least for selected kernels and NIC combinations, right? So what were the new features that were added with UCX 1.16 and 1.17 for our devices? So the biggest item probably was that with UCX 1.16 was the first release that we added support for the new MI300A and MI300X GPUs. So this involved intranode and internode testing, although I think internode was mostly tested with in the 1.17 timeline. But basically, MI300A intranode GPU to GPU performance testing and tuning was done, as well as later on testing with NVIDIA Connect X7. For MI300X, basically same intranode testing tuning as well as internode testing and tuning, both with NVIDIA Connect X7 and the Broadcom Thor2 NICs. Last but not least, within the same timeline is also that we extended our testing and coverage for the Radeon Pro, the workstation series of our GPUs, as well as the Radeon RX, which are like the client and gaming side GPUs within the same configuration. Now, UCX 1.18, currently the first release candidate, some of the things that we hope that we think that will be covered there. We don't just think we know. So there was one fix that we had to introduce in UCX for correctly recognizing the MI300A CPU, because we discovered a little bit later that it has a different CPU ID than the regular Genoa processors. And this had an impact on the inter-node communication performance. Support for our newest generation of CPUs, the Turin CPU line, has also, I think, just been merged to 1.18 series. So that is there. And last but not least, we presented last year some of the work that was done by our CPU team for memcopy optimizations for the Zen 3, 4, 5 architectures that basically allow for non-temporal transfers that bypass the caches if the individual processes sit on different CCDs. So that was merged earlier this year, and I think will be available in the 1.18 release series as well. So these are, from our side, the biggest additions in the upcoming release. Now, just a couple of performance numbers where we compare 1.15, 1.16, and 1.17 series. I'm focusing here purely on inter-node performance. So short message performance. So The very short message performance for all of these releases were roughly comparable for host-to-host memory. We found a little bit of a discrepancy once we reached like the 1 to 2 kilobyte range. And very often, because of that, we had to switch back to the no Proto V2, which basically means we disabled the Proto V2 option for that configuration. For device memory, it was a little bit higher. And this is something that we still probably need to fine-tune to see how our parameters need to be adjusted to recover the performance from that perspective, especially like the 128 bytes to 8 kilobyte range was experiencing a bit of overhead if we use Proto V2 versus the no Proto V2 versions of the of UCX 1.16 and 1.17. So this is on Connect X7 with MI300X GPUs.
Just a quick question. Is there some equivalent of GDR copy that's being used for this for the internet transfers?
Yes. So AMD GPUs are always set up with large bar support.
Okay.
And because of that, you can just do a mem copy that is, I think, roughly equivalent.
Right.
Yeah. From the bandwidth perspective, actually, that looks pretty good. And in fact, 1.16 and 1.17 look better than 1.15 for us, both on the host. So top out bandwidth is the same for all versions, right? That is not an issue. For the mid-message range, we see for host memory basically slightly better performance with 1.16 and 1.17 than with 1.15. And that's the case both for host and for device memory. So from that perspective, that's very nice. Now, performing exactly the same set of tests with Broadcom Thor 2 NICs. So the base latency is fundamentally a little bit higher, which is, I think, not entirely unexpected for a Rocky device versus raw InfiniBand. Host performance is roughly identical for all versions of UCX that we tested here, right? There's a little bit of a dip like in the 32 kilobyte range, but otherwise we get roughly the same performance out from all versions. For GPU memory, when we use device-to-device transfers, again, this is just internode. Behavior is very similar, although the area where we see the performance impact for the transfers with UCX 1.16 and 17 seems to have shifted a little bit. I am not entirely sure how to explain that, but yeah, fundamental pattern is roughly the same. And if we look at the bandwidth again, with a Thor 2 devices, the peak bandwidth is again roughly the same with all of the UCX version tested, both for host and for device memory. All right, so this is again, yeah.
Did you try to test with or plan to test with Fan 18?
Yes.
Yeah. There are a couple of changes there.
Yes, so 1.18, we just started to test, but I didn't get yet to perform exactly the same measurements, but I will do that.
Let's follow up then.
Yeah. Okay.
I have another question, like, do we have this hardware in standard in our CI/CD pipeline, Yossi? Yeah, like AMD, Thor 2, all of
We
that.
have AMD machines in our lab, but I don't think we're actually running a significant CI there currently. We had some setup issues and eventually I think we're abandoning.
So we have compilation tests, right? I don't think we run actual tests into CI. We have internal CI that we are running on the main UCX branch like twice a week.
I see. Okay. Yeah. So, and is this a preferred mode for you guys? Because the other, like we have Azure CI/CD essentially, and in theory you can install your own runners and it will trigger, full testing. Is this if you want to test and validate every commit, right?
So let's discuss that because since Azure has now our GPUs, I think there might be a way to potentially explore
Because
that
you
option.
use Azure.
Yeah.
You don't have to use Azure hardware. Like I know you're running your runners on
Yeah, you
just
connect a self-hosted agent.
Self-hosted.
yeah, you can do self-hosted CI/CD. The trick is that you need right security setup, right? Essentially, you have some runners that connects to internet, downloads code, compiles, and runs it. So
So it has to be systems with public IP addresses, I'm assuming.
No.
Not necessarily, but you must be aware that it should be a system that is probably disconnected from your internal network.
usually it's DMZ.
Mhm.
Because again, you download something from internet, run it, and okay.
So let's discuss that maybe offline. I think we have a couple of options also with some other cloud providers that help our GPUs that we have considered on whether we can integrate it one way or another into the upstream CIs. Yeah. All right. So a couple of things on things that we were wanting to tackle maybe potentially in the near future, and some of these are more like open questions. So one of the things that we have noticed is basically that on some of these platforms, the NIC is getting involved even in intra-node traffic, for example, host to device and device to host transfers, which performance-wise is the right decision. It is the fastest way to do it, but I'm not sure that that's something that we always want to have. Like very often, I think there are scenarios where you want to have the NIC basically being involved in inter-node communication, but not necessarily in intra-node. I'm not sure whether there's a good way on how to influence or disable that behavior, but I'm just throwing that out as an item. MI300A, basically with CPU and GPU cores all sharing exactly the same physical memory, also poses some interesting questions, right? Because although it's physically the same memory that has been allocated with malloc versus, let's say, with hip malloc, still are different from the operating system perspective. So even if physically it's on the same chip, from the OS perspective, they are different. And for example, system memory, system buffers that you allocate with a malloc, you cannot use it for ROCm IPC, while buffer that you allocated with hip malloc can, for example, not be used with XPmem. And that's really down to how the GPU driver, etc., is managing some of these instances. So we need to be able to distinguish them for intranode communication. But for internode communication, staging that memory, for example, through CPU buffers doesn't make sense, right? And so that's one of the challenges that we have there, that if we play around with the parameters, then we are also influencing the intranode communication pattern, not just the internode communication pattern.
So the memory type itself is not enough here?
So the memory type itself, from what perspective?
I mean, currently we have like host memory and the ROCm memory.
Mm-hmm.
So system buffer get would be host memory and device is the ROCm memory.
Yes.
But that enough? You're saying it's not that itself is not enough to decide the right thing?
It's enough for intranode, it's not enough for internode the way it seems, because for internode, it looks like the system sometimes still performs a copy to host memory because it thinks that's the fastest path.
From ROCm buffer?
Yeah.
Hmm.
And if I tune the latency values too much, then it suddenly impacts the intranode communication.
But you don't want to buffer it because it's actually on the GPU.
Because it's exactly the same HBM stack.
Hmm.
Yeah. So anyway, just throwing that out as something that.
So it's probably something that maybe we should, if we know that there's a system of HBM, probably in topology code that thinks that currently there is like a PCI topology, that there is some distance between devices.
Mm-hmm.
We should say that there is no distance. I mean that the bandwidth is always maximal between any set of devices because it's all the same memory.
Something like that. Yeah. Okay.
Also,
does it mean that like looks like XPmem? If it's in the same shared HBMM, like it's the same virtual address that everybody can access?
Yes.
So it is like almost like XPmem, just Like you have virtual address shared between everybody.
Another thing I don't think it's relevant, it's needed here, but we're also thinking to add the memory flags or specific memory type, which would be opaque from UCP point of view, but different transports like ROCm or CUDA could make use of it to do some better logic in different cases. But I don't think it's needed in this particular case.
And earlier, the copies were happening even in the presence of GPU direct RDMA.
Yes. So the way it looks like for larger messages, that's not happening, right? But for short messages, the logic somehow triggers that through the CPU memory. Yeah.
Well, because it thinks that there is no PCI switch, so the bandwidth between GPU direct bandwidth is low, so it goes to pipeline.
Yeah. So another item on the to-do list is our own NICs through the Pensando team are also being, well, they are currently being brought up. So, and we will have to revisit that also in the UCX context. I think some of the challenges that we will have there are similar to some of the discussions that were on mailing lists a couple of weeks ago with another vendor. Namely, if I understand it correctly, our software stack does not support, for example, shared receipt queues, right? So we have IV.
You mean when there's no shared receipt queues?
Yeah. So I think we either might have to go through the UD path there as well, or we might have to see on whether we can modify our C.
So the first case where such support has been requested.
Yeah. So it's something that we will have to basically see on how to handle. Yeah. And last but not least, since both NVIDIA, AMD, etc., are in the Ultra Ethernet Consortium, I think a larger question is simply what will the role of UCX be in that overall setup ecosystem, right? All right, couple of words to OpenMPI. I will be going through fairly quickly. So OpenMPI introduced support for ROCm in 5.0. And again, all the usual functionality that is required there to support GPU memory is available, although in 5.0 there's no yet GPU IPC support in OpenMPI. And if we look at some of the things that are coming up in the next OpenMPI release, so we added recently support for IPC functionality, GPU IPC functionality in the Accelerator framework, right? So that is currently implementing, OpenMPI is currently implementing that functionality for CUDA devices and for ROCm devices. And as some of the components that will make use of that is, so we modify the old BTLS and CUDA component to use this new functionality that is already there, but we've also designed a new single copy component in OpenMPI that is relying on the GPU IPC mechanism. That work is right now complete and is currently being reviewed. Hopefully we can merge it before 6.0, right? So, and again, the way this is now integrated in OpenMPI is that the SMSC accelerator component is treated by the code identical to like XPMEM or CMA. And it just that basically it recognizes if it's GPU buffer, it takes care of it itself. Otherwise, it just passes it through to the next SMSC component. And when you run it on top of UCX, that might be a little bit less relevant. But if you run it, let's say single node scenarios, this could be relevant. If you run it with the Fabric, this could also be relevant from that perspective. So this is something that is coming up in 6.0.
Just a quick question. I thought BTLS and CUDA was set to be deprecated.
It is, but it's still there, right? And the reason, because the code was complete, it was fairly straightforward to convert it from using CUDA to using the GPU IPC mechanisms. The downside of the SN CUDA component is that that component itself does not have support for single copy mechanisms, right? Otherwise, actually, performance-wise, it's still pretty decent. Yeah. So right now we consider that probably in the 6.0 series, it will be like a fallback mechanism. Yeah. So one of the other aspects where the GPU support is coming in play in OpenMPI is MPI I/O, MPI file I/O. So OpenMPI 6 already supported reading and writing buffers from GPU or to GPU buffers directly. And the way this is handled in OpenMPI is that the I/O framework basically can manage temporary buffers on the CPU side. And using a pipeline and double buffering protocol, you can basically overlap the transfer between GPU buffers and system buffers with the actual I/O operation. It's relatively straightforward. And depending on the system, you can get actually pretty decent performance out of it. So this is a test on a Lustre file system using MI250 GPUs, right? And as you can see on this graph, especially file write, at least in this context or this scenario, where the bandwidth between GPU and CPU is roughly the same as between the CPU and the NIC. If the buffer is large enough, you can basically hide the cost of the data transfer nearly completely, right? So basically you achieve the same bandwidth writing from GPU buffer than you can achieve writing from CPU buffer. Yeah, so that was already there in 5.0. In 6.0, what we are being adding is support for collective file I/O operations to improve it. So collective file I/O, again, you have some processes that also act as so-called aggregators that have a temporary buffer to perform like aggregation from the various processes. Do some work in order to adjust the layout of the data such that it matches the layout in the file. And now the question really is, if you write from GPU buffers on the aggregation side for the aggregator processes, do you perform the aggregation in CPU memory or in GPU memory? Because these are your two options. And both have advantages and disadvantages in terms of that if you perform the aggregation in CPU memory, your I/O might be more straightforward because you perform simply a write or a read from CPU memory, right? Your data transfer is device to host transfer in that case for a write operation, which often has a little bit lower bandwidth, right, than GPU to GPU transfer directly. On the other side, if you perform the data aggregation in GPU memory, you can take advantage of like the GPU IPC mechanisms that is typically much higher bandwidth, at least for intranode scenarios. But then the actual file I/O operation will have to rely on the same pipeline protocol that we discussed for individual file I/O operations there, right? So it's a trade-off. None of these solutions are optimal within this setup. If we look at some initial performance numbers, and again, no claim for generality, it's just a snapshot of what we had right now, is we found that in the current setups, most of the time, performing the transfer in the aggregation into CPU memory is slightly faster than performing the aggregation into GPU memory. But again, it probably depends on a lot of architectural details on which of the solutions will ultimately make more sense. In fact, most likely, you will find always scenarios where both of them will make sense. Yeah, so OpenMPI 5 again had support for the pipeline protocol already for blocking operations. The pull request didn't make it in time for the non-blocking write and read operations, but that will be now there in 6.0. And OpenMPI 5 again had support for using system buffer for aggregation. With 6.0, we will also have support for using device buffers for aggregation. For non-blocking collective operations, we've never tested it. In theory, it should work, and these are the famous last words before everything crashed, right? But yeah, let's see. Last but not least, OpenMPI, just a few more words. So there's a new component in OpenMPI that was also contributed by our CPU team, the ACOL component that basically allows for some specific optimizations for the Zen 3, 4, 5 CPUs, right? So basically, the Zen architectures organizes the cores in groups of I think 8 at the moment, but that might change. So you always have a certain number of cores that share level 3 cache that can be in different NUMA domains. And basically this hierarchy is exactly what the ACOL component tries to take advantage of. So during communicator creation, basically you set up subcommunicators that are focusing on this grouping. And then you have like hierarchical collectives that basically try to take advantage of these hierarchies in order to maximize the performance. In addition to taking advantage of the internal architecture of the Zen CPUs, one of the other things that the component does is actually that it can perform direct communication between the buffers within a single node using XPMEM if that is available. So basically completely bypassing the point-to-point layer of OpenMPI and perform direct XPMEM transfers. So the component is there, supports many of the more popular collector algorithms. Initial work was focusing a lot on larger message sizes. And that's the upper graph that you see over there, basically showing quite some significant improvement for like large broadcast or large all-reduce operations if you use the entire chip or the entire system. Currently ongoing work is both focusing on extending to more algorithms, more operations, but also focusing on more shorter message sizes, because especially in HPC applications, that's also quite important. So yeah, this component will also be available in 6.0. The ACOL component at the moment only supports CPU memory, so no GPU memory support in there as of this time. All right, last but not least, a couple of words for a new library that we've been working on, RockSHMEM. So this is the AMD version of the OpenSHMEM library that supports GPU buffers. And from the high level perspective, I mean, it's basically the OpenSHMEM API functionality, but with the additional ability to not just support GPU buffers for the SHMEM put or SHMEM get operations, but also to be able to initiate it from the GPU, from a GPU kernel itself. So basically, the application has a mechanism on how to completely bypass the CPU for initiating the communication operations under certain circumstances. This library was for a long time already in development by AMD Research, by a number of folks. Right now, we're in the process of basically making it like a tier 1 citizen of the communication library software stack, right? So it's a collaboration between our GPU communication libraries team and AMD Research. And yeah, so internally, the library has, RockSHMEM has the ability to use different mechanisms for the data transfer. One of the mechanisms is to use the IPC conduit, which performs basically like GPU to GPU transfer using a topic kernel. We have a so-called reverse offload conduit, which basically uses a host proxy thread mechanism to funnel the communication through the CPU side. This is to some extent like a fallback path, but also a portability path, because yeah, for various reasons. Internally, what is quite interesting and what puts it into within the context of this workshop is that the operations, the RockSHMEM put, RockSHMEM get operations are mapped to MPI put and MPI get operations. And when using UCX, basically this maps it down to UCX, UCP put, UCP get operations using the UCX functionality on GPU buffers. There's also a mechanism to perform verbs direct based GPU initiated communication. This will be focusing on InfiniBand. Initial releases of the production version will not have that feature available, but it's expected to be available at one point in the near future. But I just thought it could be interesting to basically compare the IPC conduit versus the UCX-based put-get operations. and highlight advantages, disadvantages, performance, right? So this is again running on MI300X using Intran node setup at the moment. First test using just a single thread with a single workgroup performing a ROCmem get versus and ROCmem put operations. So interesting result here. So if you just use one thread, you can clearly, with a copy kernel, not saturate the bandwidth of the Infinity fabric link, right? So for that, you would need multiple threads to perform a particular operation. And within this context, if you use the RO conduit, which basically maps it to a UCP put or UCP get operation, we see that the costs are simply more even, and you are ultimately able to achieve better performance in this scenario because that triggers the DMA engine for the actual data transfer. So you're not limited by just using one thread. It's basically triggers a DMA engine transfer for the actual data transfer, right? For if you use more threads, let's say 128 threads within a single workgroup, the IPC conduit is now basically being able to outperform, in that case, the RO conduit's performance, simply because you have multiple threads, and underneath the hood, the hardware is able to concatenate it to coalesce the individual transfer, and because of that, is able to achieve higher performance, right? The costs for the RO conduit goes quite a bit up because using this API, the standard ROCmem getmem API, what this really translates to is having 128 individual UCP put or individual UCP get operations, right? So basically, they are not coalesced on the MPI layer, they are just coalesced by the hardware for the individual load store operations. And going from there to the last, the work group-based API functionality, again, we use 128 threads with a single work group, but using the functionality that allows it to perform like a thread collective operation. There's not much change on the IPC functionality level, because on the hardware side, you can still coalesce the data for the individual load store operations, but there's a clear benefit here for the MPI/UCX version-based operations, simply because instead of now presenting 128 concurrent put or get operations, it's just one. Yeah, so the cost because of that becomes quite good. Yeah, so ultimately this is, I think, very interesting and very encouraging. So the one-sided put get operations with our device buffers seem to work reasonably well. Yeah, there's probably more work required for that perspective. I mean, including more detailed analysis and tuning of the various layers in the call stack, both ROCmem, OpenMPI, UCX, because frankly, we have not invested significant efforts yet in tuning the performance of one-sided put and get operations with device buffers. It's basically on our to-do list. Also, we plan to look at the internode performance with the RO conduit as well. And there are a number of other functionalities from the ROCmem library that need to similarly be evaluated. Yeah. Okay, that's it from my side. Any questions?
I had a question about the file operations. Are there many applications that are using file operations from device buffers?
Not yet, but I think we're a little bit in a chicken and egg problem, right? That because if you don't offer it, nobody can use it, and so it's. I know that there was some discussion with HDF5 folks, for example, whether they could use some of that functionality, etc. So I would look at it as work in progress.
I'm curious, what are your thoughts on integration with Ultra Ethernet? You mentioned we have to think about it. Any preliminary thoughts?
So I don't know. I mean, it's a good question. I mean, There are multiple workarounds, I would say, but I think the question, what is the clean solution, right? Because I mean, you could have a lib fabric UCT transport, which I know that Oak Ridge, I think, once started to work on. The opposite way around also, I mean, there's a UCX provider in lib fabric, but in my opinion, both of those are like a little bit of workaround. So the question is, what is the clean solution? It's either have a UCT transport that uses the UEC functionality directly, or I know that has also been some discussion on having UET equivalent or UET extensions sort of on the verbs layer. I don't know which of those would make more sense in a long term. Yeah.
If there's verb support, it's kind of easy. We already have precedents, right? Like verbs or direct verb support, both for MLX5. And I think we have EFA presentation later. So it's kind of solve problem to some extent. I agree with you, it will be the cleanest solution. Okay. There's a general question, where will be the recording be posted? Recording will be posted on YouTube, as we did before, and as well on the workshop page. The same, if you get slides, we will share the slides as well. Sometimes people don't share slides, but recordings will be for sure uploaded. Any more questions online?